Hey guys, welcome to today's lesson. Today we're looking at sequence and series, the general term of a GP in more detail. So this is the fourth lesson in the series, I guess you could call it, for the IB Math Studies SL. So far we've looked at a number of things, right? We've looked at the three S's, which we said was a set, we said was a sequence, we said was a series. So remember, a set was a group of words or numbers or objects, so 1, 6, 2, no particular order. A sequence was a set but has a pattern, okay, in this case goes up by 1, and a series is the sum of that sequence, okay. So that's a general aspect that we looked at. We also looked at what an AP and what a GP was. So we said an AP was, I'll do a different color, an arithmetic progression, which meant there was a common difference. Alright, so we then looked at, after that common difference, we looked something like this, 1, 5, 9, etc. So you can see that's clearly an AP. And once we looked at the AP, we also looked at the general term of the AP, which we said was, not TN, sorry, that's HSC. UN is equal to U1 plus n minus 1 times d, and that enabled us to find any term we wanted to find, basically, where UN, so U1 is the first term, n is the number of terms, and d is the common difference. We also, in that very first lesson, we looked at what a GP was, okay, and that's obviously what we're dealing with in greater detail on this lesson. So a GP we refer to as a geometrical progression. Or I guess another way we could say that is a non-linear progression. This is linear because it's a common difference, all right? But a geometrical progression, it's non-linear, so it's not having something added together that has a common difference. So 1, let's say 2, 4, 8, 16. You can see here that there is a pattern, okay, but it's not an AP, because if I add 1 to get 2, then I have to add 2 to get 4, and then add 4 to get 8, and then 8. There's not a common difference, okay, therefore it can't be linear. So what is happening, and we mentioned this in that first lesson, that we're multiplying each thing by 2, okay, to get that next term. So of course the sixth term here would be 32, okay, and then 64. Because I'm simply doubling it, I'm timesing it by 2. In other words, we said that what we actually have is a common, not a common difference, but a common ratio. Okay, in this case, the common ratio is 2. Now, how do we find that common ratio? Hopefully you remember we spoke about that. We said to find the common ratio, we simply divide the second term, let's call that U2, by the first term, U1. Or we can divide the third term, U3, divide the second term, U2. So if you're being asked to prove or to show that this is a geometrical progression, that's what we're kind of looking at. And then obviously they're going to ask similar questions. They're not going to just ask what is the next two terms. They might not ask if it's a GP, but they're going to be a little bit more specific in what they want you to do. So let's have a look at an example here. E.g. 1. Let's start with 5, and I think we use this in this first lesson, 10, 20, 40, etc. Dot, 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 ellipsis. Okay. They might say, show this is a GP. Okay, and hopefully you're thinking about how you might do that. Second of all, find the next term. And lastly, we want to find, let's say, the 10th term, just to keep things a little bit simple. So how would we do the first question? Well, hopefully if you know how to do it, you can go ahead and do it. We just said that for this to be a GP, that there must be a common ratio. Okay, there's got to be that common ratio. So we know for the common ratio, we need to show that T2 divided by T1 is equal to T3 divided by T2. In this case, T2 is 10, T1 is 5, T3 is 20, NT2 is 10. 10 divided by 5 is 2. 20 divided by 10 is 2. Therefore, we have a common ratio of 2. We've shown, therefore, I'm going to write that word, common ratio. Therefore, it is a GP. And again, I really like you to put that down too, guys. Like, I want to see you make sense that that's what we're actually doing when we're doing that test. That you're actually showing or proving that there is a common ratio. Hence, you can then say it's a GP. Of course, if it's a common difference, then it's an AP. Find the next term. Well, that's pretty straightforward in itself. We're simply multiplying by 2, so 40 times 2 is 80. Okay, not brain science. Okay. Find the 10th term. Now, we've got U1 here, we've got U2, we've got U3, we've got U4, we've even found U5. I guess we could keep on timesing by 2 to get U10. But if we just do that in the calculator, there's no really reasoning or no working that we can show. So we need to be more specific, I guess. Now, I'm going to show you this in a more generalized form, just like we did when we first looked at the AP. Okay, so the first term we know here is U1. These colors are not working too well for me today. U1, right? The second term is U1 because it was the 5, but then we multiplied it by 2 because that was the common ratio. The third term, U3, was, well, it's the second term, and I times it by the common ratio. So I'll call that U1, call that U2, call that U3. So U4 would be what U3 was, so U1 times R times R times it by that common ratio again. I hope you start to see what I'm developing here. Okay, if I want to have a formula for UN, okay, just like we did for the AP, what's common in all these things? Well, hopefully you recognize that there is a U1 in absolutely every single one of those 4 terms. So U1, and that was quite similar if you remember for the AP. But what's happening now? Well, in the first term we just have U1. It's the first term. The second term we have this times R. In the third term we have times R squared. In the fourth term we have times R cubed. So hopefully you can see that we're multiplying it by a ratio. However, it is the power of n take away 1. 4 take away 1 is 3. 3 take away 1 is 2. 2 take away 1 is 1. Theoretically, 1 take away 1 is 0. Okay, and what we've now come up with is the fanciful general term of a GP. Okay, this is the general term of a geometrical progression. Okay, and just like we saw with the AP, we can answer this. Now, if I want to apply this, of course, to this question, all right, we've got U10 is equal to the A, and the A is 5, so the U1, and that is 5, times the ratio, which is 2, and 10 take away 1 is 9. Okay, and now on my calculator I can type in 5 times 2 to the power of 9 to get my final answer, which I think is 2560. 2560. I hope. I don't have a calculator there, so hopefully that's right. Okay, and that's pretty much it, guys. Look, of course, there are some more challenging questions. Just like we saw with the AP, we could see that that actually could happen. And what are they looking like? Okay, so let's have a little squeeze at one of them. Okay, so example 2. We're going to put here x plus 1, comma, 5x minus 1, and 10x plus 7. And we're going to say that this is a GP. Find all possible values of x. Alright, so we've been told in this case that this is a GP, right? So because it's a GP, we know that R is equal to, MI rate, U2 divided by U1, which is equal to U3 divided by U2. That's our kind of whole proof of what a GP is going to be. So just like we saw with the AP, we're going to solve this by substituting these values in. 5x minus 1 over x plus 1, that's equal to 10x plus 7 over 5x minus 1. And what we've now got is a quadratic equation. Now, unfortunately, because this is going to be a quadratic, when I times this by x plus 1, that's going to be a square, we can't use the F3 solver. Alright, it's only going to give us one solution. So we're going to need to put this into F2, which is the polynomial, alright, to the power of 2, of course. The issue is going to be that we need it in the form of ax squared plus bx plus c is equal to 0. So I can't just have it in this form. We need to go that other step more further. So I'm going to put here 5x minus 1. Now I'm going to times this by 5x minus 1. Alright, but I might just chuck a square in there because that's what it is. I'm going to times the right hand side by x plus 1. I'm going to have 10x plus 7 and then x plus 1. And so the process will be, of course, will be to expand and simplify and put it all to one side. So here we're going to get 25x squared minus 10x plus 1 equals 10x squared plus 10x plus 7x plus 7. I'm going to throw it all to the left hand side. That ensures I have a positive x squared, but you know what, it probably doesn't matter. This is going to be 17x, by the way, just so we can do things a bit quicker. So I'm going to take 10x squared across here. I'm going to take the 17x across here. And I'm going to take 7 across here. So I'm going to end up with 15x squared minus 27x, and then we're going to have 1 take away 7 is negative 6 equals 0. Okay, from this point forward, we have got it in this ax squared plus bx plus c equals 0. So we can go ahead now and solve this via that F2 polynomial solver by entering the numbers 15, negative 27, and negative 6. Alright, so go and do that. Now, once you've done that, because it's a quadratic, there's a good chance you're going to have two answers, right? And in fact, we do. If we solve all of that, okay, what we're going to come up with is x is equal to negative 1 on 5, or x is equal to 2. Okay, hopefully you can see that. It's a bit hard there. I said my colours don't seem to be popping out today. So we've got those two solutions, and that's correct. We can have two solutions because when I substitute them in to the series, we're going to see that we're still going to have that geometrical progression. Okay, it can be a negative. Absolutely, it can be. It can work. And I encourage you to sub it in to have a look at it as well. I'm not going to do that just yet. Okay, so that's a hard question, right? And the hardest question, I guess, you come through would be something to do with this. I don't know, I'm going to make one up on the spot. So something like this for my third example. Let's say I've got the progression, I don't know, 3, 6, 12, 24, ... And it says find the first term over 100. Okay, we saw that for the AP. Okay, so for a question such as this, and it is quite challenging, so please bear with me, the first process means I need to identify, is this an AP, is it a GP? They haven't told me. So in this case, we know that it's plus 3 and then plus 6, so it's not an AP. If I times it by 2, times it by 2, yes, it's going to be a GP. So we can state there's a GP. Why? Because U2 divided by U1 is equal to U3 divided by U2. Alright, which in this case equals 6 on 3 equals 12 on 6, which equals 2. It also helps me identify my ratio. Okay, my common ratio. So that's really important. If they don't state that this is a GP, guys, it's very good practice to make sure you say that it's a GP. I go ahead and go, okay, well, we know for a GP, what do I know? What have we been taught? So far, we've been taught this. UN is equal to U1 times R to the n negative 1. So it's a formula. Now, we're looking for the first term over 100. What I'm going to do, I'm going to put 100 equals, okay, to see what the term's going to be. I'm going to put U1 there for R. I'm going to find the ratio we know is 2 to the power of n minus 1. Okay, and then what we've actually created here, unfortunately, is an exponential equation. Why is an exponential equation? Because we're solving for a power, or in other words, i.e. an exponent. So therefore, this is what we refer to as an exponential equation. Now, of course, exponential equations are challenging, and without the correct calculator, it would be almost impossible unless we knew how to deal with logs. But I'm going to deal with this as we would in our other equation. Opposite of times 3 is divide by 3. Okay, so 2 to the power of n negative 1 is equal to 100 on 3. And then, you know what I'm going to do? I'm going to go all the way to my F3 solver, and I'm going to sub that equation in, and it's going to let me know what n is equal to. It's as easy as that. It does allow you to solve exponential equations, which is quite remarkable. We get, what is it, 6.0588 ... ellipsis. Now, of course, n must be an element of a positive integer. Okay, therefore, n must equal 7. Now, it says find the first term over 100. So what I'm now going to do is go find the 7th term. So we're going to go back into our rule that we were doing up here. Okay, and I'm going to say that U7 is equal to U1 times the ratio of 2 to the power of 7 take away 1, and the answer comes out to be 192. Alright, so that again is a pretty challenging question, but hopefully you can see the relationship between that question and the one we did for the AP, because the structure, the steps that we've used to take it has been absolutely identical. Yeah, look, it's a hard question, as I said, but hopefully you can see the pattern of these questions and you can start applying it. So just as a quick recap, what have we learned today? Okay, well, particularly we went through the nth term, or the general term of a GP. Okay, first of all, why is it a GP? Well, we have that common ratio, i.e. we know that U2 divided by U1 is equal to U3 divided by U2, or vice versa. That was number 1. And then we learnt the rule, as I said, for the general term. UN is equal to U1 times, it's not very good times there, is it? Multiplied by R to the n negative 1. Okay, and then we can get those harder questions on top of that. Look, guys, sorry for the long lesson. Hopefully you've got a bit of an idea about now how to find the general term of a geometrical progression, and certainly how to prove that it is a geometrical progression, and those harder high-level questions which we need to be able to attack if we're going to get a 6 or a 7 in our IB course next year. Drop me a line if you have any problems at all, guys, on email. Otherwise, have a great day, and yeah, I hope this made it a bit useful for you and made sense. Thank you.